looking at binomial distribution. So, looking at probabilities of things that either happen or don't happen, pretty much, right? This is what we're going to learn about in 4.2. We won't get to all this today. Just a lot of it, though. We're going to start by talking about a binomial experiment, or a binomial setting. What is it for a setting to be binomial? It has to conform to these things. So we're going to have to check all of these conditions before we can go on and perform calculations and things like that. So we've got some variables that we'll talk about. With these, we got n, number of times each trial is repeated. We got p, the probability of success for each trial. We got a q, which is the probability of failure. And then we've got this x, which is going to be essentially the number of successes that we get. All right, we're going to get some problems to get this stuff all in the context here in a moment. So we are going to always check bins, okay? So, and we'll do that here in a moment. It's very important that you know what bins stands for, okay? B, is it binary? Is there clearly a success or a failure, right? If your answers are red, green, or blue, then no, it's not success or failure, right? Either red, it's green, or it's blue. Right. Independent. Alright, so let's just say independent. And then we're gotta know there's a number of trials is fixed. And the success, the probability of success is the same for each trial. Alright? And we will go through bins a bunch of times as we go through these examples. Alright, so let's check it out. Let's check to see if these things are binomial or not. Alright? Here we go. Alright, so we are going to check our bins. So I call it checking the bins, right? Is it binary, this situation here? Talking about a surgical procedure, it's got 85% chance of success. Performing this procedure on 8 patients. So, is each trial either a success or a failure? That's what the B stands for. Yeah, either the surgery goes well or it doesn't. They have a way to say that it's successful or a failure. Alright, I. Is each trial independent? In other words, the fact that one surgery goes well, does that affect the probability that another surgery goes well? Or are they totally separate? Given that it's not the same doctor, right? If it's not the same doctor, you would say that those are independent, right? And if Dr. Frankenfurter does a surgery and has a success, it doesn't affect Dr. Comedina's success for surgery, although he is funky. Kind of an old school reference joke. The funky Comedina. But okay, so N. Is there a fixed number of trials? He's doing it on only 8 patients, right? So yes. And then is the probability of success the same for each trial? Yeah, the surgery has an 85% chance of success. So there we go. Now we're going to identify what is N, P, Q, and X on this thing, all right? So N is the number of trials. How many trials? 8. P, what's the probability of success? 85. So we're going to express that as a decimal, 0.85. How about Q, the probability that it's not successful? Well, the probability of it not being successful is 1 minus the probability that it is successful, right? Z complement, or 0.15. And now we'll look at X. What are our proper what are our different values that X can have, right? So what we're saying is, how many different successes could there be, right? Well, it could be a lot of different things, right? The doctor out of 8 could have 0 successful surgeries. Maybe you shouldn't be practicing medicine after that, but then he could have 1 successful, he could have 2 successful, 3, 4, 5, 6, 7, all the way up to 8, right? Those are all the possible values of X, and they each represent how many of the 8 surgeries were successful. That's what that is. Alright. Let's do it again. Oh, this is the answer. I also can't help you with weight loss, but I have 2 million pencils. Not literally.
Okay.
I'm here for you for some things, and other things, I just can't provide.
Thanks, bud.
So, let's determine if this is a binomial setting, or a binomial experiment. I would like to say a binomial setting. I think makes a little more sense. Okay. We got a jar with 5 red marbles, 9 blue marbles, and 6 green marbles. You're going to randomly select 3 marbles from jar without replacement. The random variable represents the number of red marbles. So we're going to be looking at X, right? Is how many red marbles we pull out. We're going to select 3, right? So that means that X should be 0, 1, 2, 3, and that's it, right? So let's first check bins. Is it either you got a red marble or you didn't? Yeah. So that checks. Are the trials independent? In other words, if I grab a red marble the first time, does it affect the probability that I grab a red marble the second time? It does, because I'm not replacing them, right? The first time, yeah, since I'm not replacing them. So, right away, we're going to say, it is not binomial. Okay? This is not a binomial set. That's right in cursive. It's really bad at cursive. Go back to printing. Okay. Huh? There you go. Hey, what the heck? Okay. We're going to take a multiple choice quiz that consists of 10 questions. Hey.
Or the binomial thing, maybe since we're just like adding and subtracting what's left, I could just do E and then
For the last one?
yeah, like for your doctor one, the 15. I already got that before.
Yeah, you don't have to. Yeah, you don't have to like write it down. It's okay. The Q. Yeah. All right, let's see. First of all, let's see if this is a binomial setting. The multiple choice question test. 10 questions. 4 possible answers per question. You're gonna randomly guess the number to each question because you did not study. And you don't even understand the words on the test. So you guess. Okay. So is it binomial? Is it binary? I'm sorry, the setting. You either get a question right or wrong, right? If X is the number of questions you get right, then that checks out. So you're looking at a multiple choice test, right? The fact that you got number 1 right does not increase your chances or decrease your chances of getting number 2 right, right? So that means that they're independent. Is there a fixed number of trials? Yeah, for sure, right? There are 10. You're going to go through the 10 questions, see how many of those you get right. Is the probability of success the same for each trial? Yeah, it's 1 out of 4. What if the last 3 questions were A, B, C, D, E, F? This would no longer be a binomial setting. But since they're all 4 possible selections per answer, it works. So then, what is N? 10. That'll be 10 trials. What is P, the probability of success on 1 trial? 1 out of 4? Which is the same thing as 0.25. But how about Q, the probability of failure? It's going to be 1 minus 0.25 or 0.75. And how about X, our random variable? What values could it take on? Well, anything from 0 all the way up to 10. We did it. So, we've got this binomial probability formula. You've got your binomial coefficient multiplied by exponential stuff. Now, it's great to know this, but we're gonna get our calculators to do this for us. Huh? So it's good to see the formula. We're gonna have our calculator do it. Alright, so we're gonna use the TI Inspires to do this. And I'll show you how to do it. That's actually it right now. Here we go. Microfracture knee surgery has a 75% chance of success on patients with degenerative knees. They're degenerate knees. This surgery is going to get performed on 3 patients. We're going to find the probability of the surgery being successful on exactly 2 patients. All right, exactly 2 patients. So because it's exactly 2 patients, we're going to use binomial PDF in our calculator. But first of all, let's not get ahead of ourselves. Let's first see if we're allowed to use the binomial distribution in order to calculate this probability. So, first of all, is it either success or failure? Is each trial either success or failure? If one surgery goes well, do you think that increases or decreases the chance of the other surgery going well? No. They're probably unrelated. Is there a set number of trials? Definitely, they're only going to do it 3 times. And is the probability of each trial the same? Probability of success of each trial the same? Yeah, it's 75% chance of success no matter what. Okay, so now we're going to determine what n is. And how many trials are we going to do? 3. What's the probability of success for a 1 trial? Yep, so 0.75. And now we're going to ignore Q. If we're going to use this, if we're going to do this using the formula, we would need Q. But we're going to use our calculators. So all we need is X. How many trials do we want to count as successes? 2. So now that we have this information, we have enough to go to our handy-dandy calculator and calculate this probability, all right? So you're going to get out your calculator and you can do this just using the scratch pad, right? So hit the calculator button, use the scratch pad, and in order to do this calculation, we're going to go menu. Go to probability. And now we're going to choose distributions. This is a binomial distribution. We're going to go down to binomial PDF. Okay, enter. And now it's going to ask us for those things that we just wrote down, right? Yes. So how many trials are we doing? 3? We're going to perform the surgery 3 times. Probability of success is 0.75. What's the probability that 2 out of the 3 are successful? That's what we're being asked. So n is 3, p is 0.75, x is 2. So the probability that 2 surgeries are successful is approximately 0.423. Sounds not great. Those are not good odds. All right, so how do you write your answer? You are free to write your answer like this. We're going to put what we put in our calculator. So it was 3.75 2. What was that equal to? 422, right? I said 2, 3. So that is an acceptable way to express your answer. It's good enough for a college board on an AP statistics exam. I think it's good enough for us as well. So that would be an acceptable way to write that. All right. So we use the calculator. Another method of doing this would be to draw a tree diagram. That does not sound that awesome, right? Another method would be to use the formula. Also does not look that awesome. The calculator is definitely the most efficient way to do this. Alright. So that's the way we're going to go with. We're going to go with the calculator method. So, we got a card. Gets pulled from a standard deck and replaced. We repeat it 5 times. We're going to find the probability of selecting exactly 3 clubs. First of all, before we can use our binomial PDF function on our calculator, we got to check our bins. Is each trial either success or failure? Yeah, either you got a club or you don't, right? There's no gray area there. Each card is being replaced, so are the trials independent? Okay. Are there a set number of trials? Yeah. Totally 5 times. Is the probability of success the same for each trial? It is, right? Yeah. Yeah, as long as you're replacing it, right? It's going to stay the same. Alright, so then what is N? Our number of trials. 5, right? We're doing it 5 times. How about the probabilities of success? Huh? Yeah, there are 13 out of 52. And there are 4 sets of 13 and 52, right? Which means that that's 1/4 of it. You could put the fraction in your calculator. You could put 13 over 52 in your calculator and it'll be fine. It'll still calculate it. I will do it that way just to show you that it works. And the one's X. And how many successes are we looking for? Yeah, we're looking for 3. Alright, now we can go ahead and put that bad boy into our handy dandy calculator. So we're going to go menu, probability, distributions, and we'll go down to binomial PDF. It asks us our number of trials. We're doing 5 trials, right? Probability of success, I'm actually going to put as 13 divided by 52. You don't have to simplify your fractions or make them decimals. It will calculate it based on this fraction value. We're looking for the probability of 3 successes. You hit enter. And we get approximately 0.089. Okay? 0.089. So I would say binom PDF 5 13 out of 52 comma 3 is approximately 0.089. Is that what we got? 88, sorry. Alright. And there it is. And again, if you wanted to look at taking a formula approach, that is there. If you were to put this in your calculator in the blue, you put that in your calculator You would get the exact same number of ions. Alright. Here we go. So let's talk about a probability distribution. So this is our microfracture knee surgery. And how was this calculated? I mean, how did you get this thing, right? Well, it turns out, what this is saying, this is the probability of 0, right? First of all, what is it? So if you wanted to get this number in your calculator, you would do binom px. Um, 3, comma, 0.75. Okay? So it's the probability that you get 0 successes out of 3 surgeries. So we're going to be able to construct one of these using our calculators. It won't be too bad. We'll do it in just a second. Alright. Let's construct probability distribution. Let's do it. Yay! Alright. Okay. Yeah. It's really weird because I'm trying to find the probability, right? They're asked why they liked texting on their cellular phones. 7 participated, said they randomly selected, and after they liked why they liked it better than calling. So here it is. It turns out that it's in the picture. 56% said that it was quicker than calling. I think that's supposed to look like a phone screen from 2005. And we will pick this up when we come back.